So the first thing we wish to do when we encounter any kinematics problem is to define a coordinate system. And so I'm going to define up as positive and to the right as positive. And the first part of the question states that the ball, which I'll indicate with a red dot, passes the window at a height of 18 meters above the ground. And it passes with a vertical velocity of 14 meters per second squared. So I've assumed that the ball is passing the window at some angle that we don't know, and I'm breaking up that velocity into its x and y components, and I've labeled the vertical component to have a speed of 14 meters per second. So next we need to write down our kinematics equations, and so I'm going to briefly reference them here. So we have that so one thing about the kinematics equations is that every equation is assumed to only be concerning one component of a direction. It can be any direction, but it is only referring to itself as one direction, meaning that if I have d and vi, so let's say I'm writing the first equation, d equals vit plus 1/2 at squared. The a, the vi, and the d are all referring to one specific direction in planar coordinates, meaning that this d is only referring to how far it travels in the x. This vi is concerning the initial velocity in the x direction, and a is referring to the acceleration that the object is feeling in the x direction. But I can also re-express that and say that for any direction, meaning I can say that this is the distance traveled in the y, the initial velocity the object feels, the object exhibits in the y, and the initial acceleration this object, the acceleration this object experiences in the y direction. So the point is that it's only referring to one direction, and that's true for all kinematics equations. So I'm going to write the rest of the kinematics equations here. So we have vf squared equals vi squared plus 2ad. We have vf equals vi plus at, and we have d equals vi plus vf over 2 times t. Okay, so now we wish to determine what was its initial speed. So let me figure out how to scroll here. Can you not scroll? Oh, here. It's refusing to grab. There we go. Sorry about that. Okay. So we should determine the object's initial velocity. And so we want to determine which kinematic equation we wish to use. And so in this case, we know that the final velocity, and final can mean at any point in the trajectory. So in this case, we're looking at the final velocity as 14 meters per second. So we have that piece of information. We know how far it's traveled in the y direction, which is 18 meters. And so when we look at equation 2, we see that we know vf, as we just stated, is 14 meters per second. We know d is 18 meters. And we know the acceleration due to gravity is the acceleration that the object feels in the y direction. So we have, I'm just going to rewrite it, vf squared equals vi squared plus 2ad. And so we just plug in our numbers. 14 squared equals vi squared plus 2, and now this is the important bit, and this is why we defined a coordinate system, is because the acceleration that the object is experiencing is in the downward direction. And so according to our coordinate system, that means that the acceleration we express in our equation should be a negative number. Whereas the other values that we've put, namely VF and D, are going to be positive. So we have negative 9.81, and I'm omitting units for brevity, but technically you should include your units in your equation, especially if your teacher is going to remove marks if you don't. And D, which is 18 meters, which I'm omitting. And so when you solve for VI, you find that VI equals 23.43, and the final answer, you should always include your units, meters per second. And if you include your units, you'll find that, in fact, meters per second does come out. And so this is the initial velocity that the object that the object exhibits at the time it was thrown, or at ground level. And so in the next part of the question, we wish to determine what altitude the object reaches. And when I read this question, I interpret this as the altitude from ground level and not from the height of the window. And so at this point, you have to think for a couple of seconds, or if this is your first time, maybe a minute or two, and understand that when the object reaches its maximum height, we can make a statement about its vertical velocity. And that is, we can make the statement that VF, or that the vertical velocity, is 0. Because when an object is traveling through the air, it is thrown at some angle until it reaches its maximum height, and then it begins to fall down due to gravity and hit the ground again. And so at this point, the object's vertical velocity, Vy, is equal to 0. That is, the y component of its velocity is 0. And so we make that statement about the object's vertical speed, and we plug it into a kinematics equation in which we wish to determine the unknown. So we wish to determine how high it was thrown from ground level. So we just determined VI at ground level, so that's probably going to be useful. And we see that, in fact, this equation, number 3, we have VF, VI, equation 2 rather. VF squared equals VI squared plus 2AD. We know A. We wish to determine how high it will reach from ground. We know VI, and we know VF because we just made a statement about it, and VI was determined in part A. And so I'm going to rewrite the equation. We have VF squared equals VI squared plus 2AD. And once again, we say that VF will be 0 at its maximum height. VI was what we determined in the previous part of the question, is 23.43 meters per second, and once again I'm omitting it for brevity, plus 2, and once again negative 9.81, because gravity, the acceleration due to gravity is acting downwards, meters per second squared, multiplied by d. In this case is the displacement between VF and VI. And of course, once again, it's only concerning the vertical displacement. And so I'm going to put delta y so that becomes clear. And so when we solve for delta y, after some algebra, we find that delta y is equal to 27.99 meters. And so this is the height at which, I guess a better way to say it would be the maximum height above ground. The maximum height above ground, the object will reach. And in part C, we wish to determine when it was thrown. And so once again, we go back to our kinematics equations. So we determined VI, which may be useful, and we look for an equation in which we can determine the time at which it was thrown. And in this case, we're trying to determine the amount of time it took for the object between when it was thrown to when it passed the window. So this amount of time. And so from our kinematics equations, we can see that since we know VI and since we know VF, which is 14 meters per second, VI we determine in part A. A is the acceleration due to gravity in the vertical direction, and T is what we wish to find. We see that equation 3 will be most useful. So VF equals VI plus AT. So VF equals VI plus AT. And VF is 14 meters per second, which I'm omitting units once again. VI is what we determined in part A, which is 23.43 plus negative 9.81 meters per second squared times T. So delta T in this case is the amount of time between VF and VI. So delta T is time between VF and VI. And so when we do some algebra and solve for T, we find that delta T is 0.96 seconds. And in the last part of the question, we wish to determine when the ball reaches the street again. And so once again, as in part B, we need to take a second to think about what that means, what that statement means mathematically. And when does it reach the street again is akin to saying that the vertical speed that the object is experiencing when it reaches the ground will be the same as the initial speed that the object feels when it reaches the ground. In fact, there's a couple of ways to solve this question. And another way is to determine the time between the object, how long it takes for the object to reach how long the time between when the object was thrown and its maximum height, and multiplying that by 2. Or we can instead say that the initial velocity in the vertical direction is equal to the velocity in the vertical direction when it reaches the ground. And so we're going to use the second method. And so we know that VI is 23.43 meters per second, as we determined in part A. We know VF now is the same when it reaches the ground. This statement, by the way, is simply due to conservation of energy. If I throw the object with a certain amount of speed, it has a certain amount of kinetic energy. And as it reaches the top of its trajectory, it will have gained some potential energy. And when it reaches the top, it will have no more kinetic energy. And, well, due to its vertical velocity, it will have some kinetic energy since it's moving across the screen. But that kinetic energy that is lost will now be in the form of potential energy. And as it reaches the bottom of the trajectory, all of that potential energy will have converted back to kinetic energy. And so its speed in the vertical direction should be the same. And so we're going to use equation number 3. So VF equals VI plus AT. And so VF would be minus 23.43 because it is now moving downwards. And VI would be 23.43 meters per second, positive, minus 9.81 meters per second, or it would be plus and minus negative 9.81 meters per second squared, multiplied by t. And so when we solve for t, we find t is equal to 4.776 seconds. And that is the time between when the object was initially thrown and will once again reach the same vertical speed and hit the ground again.